hello. Welcome. If you are joining, thank you so much for joining live. If you're seeing this later on as a video upload, live replay, also welcome so much. Thank you so much for joining, for watching all the way through, or for watching at least some of this and saying hi in the comments and sharing your thoughts in the comments as usual. We look forward to reading your chat messages, seeing everything, all of the thoughts that you will share on this live. And if you're already in bed, well, hopefully you have sweet dreams. And hello, Chickpea Break is here. My goodness, Chickpea, Acacio, all my best friends on these lives are here. Oh my God, Acacio59 says hi. Acacio, ¿cómo estás? Hello, hola, how are you? Chickpea, how are you doing? How is your health? I read your comment somewhere where you said that before, or because of sleep issues, you are going to bed early, and I want to support you in doing so as many of the days as you need to. I'm very happy to see you here tonight indeed, but if you have to go to bed, we understand, and you can always see these later on as a video upload, as a live replay, like I was saying. But indeed, we have missed you very, very much. Oindris Chickpea Break, best mod is here. Indeed, Chickpea Break is the best mod. Very supportive of you to join. Thank you so much. Can we get 20 likes? Oh my God. Let me pin that. It's so nice to see you guys. Muy bien, amiga mía. Hello. Hello. Hello, Sage, your mom. I'm sorry to hear about that situation. Sage, your mom. Good luck with everything. Chickpea Break says, I'll be here tonight for the action. Oh my gosh. So Chickpea Break, tell me everything. How are the Bahamas? You are in the Bahamas, right? You're in some sort of very beautiful island, if I remember correctly. So tell us, how is everything? How are the islands? How is the ocean? How is the Caribbeans? Hello, Michael. Michael says hi. Hi. Hello. Hello, everybody. Can we please get some likes? Can we please get some double taps on that screen of yours, on that beautiful screen? Let's get some double taps. Let's get some super chats. Oh my gosh. Chickpea Break, since you're here, can you ask intermittently, in fact, quite regularly, for people to give super chats? That would be amazing. That would be most amazing. That would actually boost my confidence and my mood and my abilities to tell you so many things, so much more. Michael says, you're so beautiful. Well, thank you, Michael. Thank you, everybody, for being here and for liking the live. Tonight, we're going to talk about cosmology once again. So yesterday, we had a most satisfying discussion about cosmology. And of course, we talked about the early universe as well as the evolution of the universe, really. And we saw how sort of we have an input, which is the cosmic microwave background radiation map, and then we have the output, if you will, if we look at the galaxy map and trying to kind of connect the dots in between and such. So we had a lot of fun talking about that. I'm in the Bahamas and it's been raining a lot. Oh gosh, Chickpea Break, is it raining a lot? But it's only an afternoon shower, right? Or are you guys getting storms? Michael says, of course. Thank you, Michael. Thank you, everybody, for joining. We're just getting started, saying hi to everybody, and we will be continue with the, oh my gosh, we will be continuing to continue with the cosmology live. Acacio, Acacio did a super chat. Oh my gosh. Muchas gracias, my friend Acacio. Let me like and heart that so very much. Heart and liking of the super chat that Acacio has done. Acacio, you are a most generous and supportive viewer of these lives. So thank you so very much indeed for being here. Oh my gosh. Oh, what are these? $30. What is this? What is this? Can I like it? Can I heart it? I'm seeing some things move around in my screen. Excuse me. Sometimes I have to figure out what is going on. Thank you, Ocasio. Thank you. $30 super chat for a chickpea. A ponytail is more like $500. How could you? How could you decrease my value like that? Thanks, Ocasio. No, please ask for more money than that. And we're going to be discussing cosmology, guys. We're going to be discussing cosmology, not cosmetology, nothing cosmetic here. We are generally not in the need of too many cosmetic stuff on these lives. We generally talk about physics with a focus in cosmology, astrophysics, particle astrophysics, and astronomy, okay? So in this channel, we present kitty cats, my children who are cats, and myself, my face, indeed, and we talk about physics, including but not limited to, including but not limited to, of course, astrophysics, particle astrophysics, cosmology, one of my favorite topics, astronomy, and such, particle physics, if I did mention that. Welcome, everybody. Welcome, welcome, welcome. Welcome, Asia. Welcome, Africa. Welcome, North America. Welcome, South America. Welcome, Africa again, because I just love Africa and I would love to go to Africa. So if you're from Africa, put a little hearty heart in the chatty chat. Welcome Antarctica, my other favorite continent. Welcome New Zealand. Welcome Australia. This time I will say New Zealand first before Australia because those poor Kiwis, poor sweet, sweet people. You know, New Zealand people are really the sweetest, just the sweetest. I mean, most people outside of America kind of hate Americans, but I will say that the people in New Zealand are so sweet to us. They're so understanding of our difficulties. And they generally avoid, they generally don't rub it in our faces. And they have been most kind to me. So welcome New Zealand, welcome Australia. Welcome one, welcome all. Let's get this live started. Welcome Caribbean, welcome Madagascar. Before I forget. Hello, my loves. Hello, Lethal Wolf. Hello, Islam Umarov. Hello, Acacio. Hello, Bran. Hello, Michael. Hello. Hello, Islam. Hello, Lethal again. Mike D. Oh my gosh. Mike D saying I fell in love with another lady on YouTube. Sorry, that's totally fine, Mike D. You go ahead, my love. Go ahead. Go ahead. I give you my full blessing. Before you go, do you want to do a $500 super chat? Oh my gosh. David is saying, what is your opinion of the inflation theory? Can you provide a visual breakdown of the CMB map and its features? Africa is hot. And then Mike D is saying, lol, lol. Well, Mike D, because you're breaking all of our hearts all at the same time, do you want to do a super chat? You could do $500 or $50 super chat, whichever is better for you. Whichever. Some people like to give more. You know, they're giving people. I was reminding you of Madagascar, but you just mentioned it. Exactly. I've got it. Madagascar, welcome. Sicily, welcome. Caribbeans, welcome. Welcome. New Zealand, welcome. Any other? Sri Lanka, welcome. I'm thinking of islands, island countries. Singapore, welcome. Bahamas, welcome. Especially Bahamas, welcome, because my favorite mod is from Bahamas. Oh my gosh, chickpea break. Ever since that I've learned that you're from the Bahamas, I just cannot. Nice to be together, says Lethal Wolf. Hello, Lethal Wolf. So that was a great question, David. Let me come back to it. And I don't know if I can give you, I don't know if I have visuals for, actually, you know what? No, I may have a CMB map somewhere. So let me show that to you. That's a good point that David has made, which is that we should probably see a map visually of the CMB. So indeed, that's a great point. We might, towards the end of the live, do that tonight. You might want to remind me one more time, David, if we don't get there. But indeed, we should look at a map of the cosmic microwave background radiation, like Salam, nice mic drop. You just yak and squeal. Ma salam. Thank you, David. Eversor said, Eversor. It's like professor, but Eversor. Eversor is here, my friend. Eversor, how are you? Saying my favorite professor. Oh my gosh, Eversor. Well, thank you, thank you, thank you. $200 super chat for chickpea eating mukbang while class is in session. I just ate the chickpeas, my friend. I just ate it. We are discussing cosmology. Join us and chat. I will say in my details page. How about that? Okay. Oh my gosh. Oh, and please do like and sub. How about that? Oh, I still had caps lock on. I'm actually going to do that. I need some likes and I need some subscriptions, guys. Like and sub. Like and sub, please. Chili, Chili shot orbitus. Chili is here. Chili shot orbitus is here. Good morning to the UK. If you're from the UK, I seem to remember you might be. Because Chili Shot, I think, was the one who did a super chat last night and was in pounds. It was in pounds. Liked and subbed, yes! Dan, you had the money-making idea already. I did. All done love says, oh, did you like the live? Oh, God. Liked and subscribed. Okay, good. Very good. Thank you once again, Acasio. Anybody else who wants to do a super chat, feel free. Feel free. Feel free. Feel free. Feel free to super chat. Okay. So now let me talk about the topic of the day and give you some value out of this live stream. Okay. So I named this live stream Modern Era of Physics because we're going to be discussing the theory of everything, or if there is a theory of everything, question mark, question mark, question mark, as we sometimes do, of course. Remember, all of that discussion about superstring theory was really because superstring theory is motivated by being a candidate for the theory of everything. Some theory that can subsume all of physics and explain all of physics in a broader, more liked way. Because there were parts of physics, some big, extraordinary, up and coming, extraordinarily different, insightful, and sort of breakthrough sorts of things that happened in the 20th century, which also did not see eye to eye. So there's an eye here and there's an eye here, and they did not see eye to eye. Okay. So these were namely, of course, general relativity on the one side and quantum mechanics on the other side. These two sides of physics were not seeing eye to eye, were not quite unified by something broader, bigger, better, sort of this mother cruise ship, if you will, that can kind of subsume all of these little boats underneath it and let everybody sail and let everybody have a rhyme and a reason and a method to the madness. So even though these theories, even though these pieces of work, not even theories, because a lot of these things have also been proven out, they've been shown with experiment, they've had tremendous experimental success in each of these fields, but yes, they do have certain drawbacks, certain little flaws, if you will, or certain limitations. Both are not totally correct. And they don't see eye to eye. The people who generally work on these things, on the one side, general relativity or classical physics, if you will, classical as in it's not Newtonian mechanics, it is a correction to Newtonian mechanics to give us a theory for gravitation, but it is also not quantum mechanics. It is not the theory or the physics of the very, very small. So the physics of the very, very big, general relativity, and the physics of the very, very small, quantum mechanics, on the two sides don't agree. But there were both gifts given to us in the modern era of physics. So if you're ever taking a class called modern physics in your undergrad or grad or wherever, even if you're not a physics major, you might come across this class. It's called modern physics. At least when I was in school, this was often offered at various types of programs. And pretty much modern physics, that's what we mean. It's the physics that was that came up and that got worked on and that got contributed by various very amazing, outstanding scientists, primarily in the 20th century. Really, what you end up studying is mostly the 20th century stuff, right? So the early 1900s are very important. The 1905 year, extremely important. Very, 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 very important. Einstein gave us four tremendous contributions in that year, including, of course, but not limited to, special theory of relativity. So this, general theory of relativity is not always taught in college physics, in undergrad physics. It is actually a sort of a not compulsory class. It's an elective, a special elective, even in grad school, right? But special theory of relativity is, of course, taught in undergrad. If you take something like modern physics, you will get a flavor of that. So pretty much this whole situation with relativity, which special theory of relativity then goes on to give us general theory of relativity, of course, which gives us the theory for gravitation. That is what we're putting over here. It's the classical physics. And then on the other side, what happened in the 20th century, of course, was developments in quantum mechanics or quantum physics, which is the physics of the very, very small, giving us things like atoms, the physics of atoms, subatomic things, the nucleus, what's within the nucleus. Things are getting discovered even within the nucleus in the 20th century that we knew not of prior to then. We thought the atom might be just it. That might be it. I think atom is a Greek word. Somebody can look up the word atom. I believe it kind of means sort of the smallest foundation of stuff. But please do look this up. Somebody in the chat can look it up right now. The meaning of atom, I do believe it comes from a Greek word. So people literally thought they were ready to, accept the atom as the fundamental block of matter, fundamental little unit of matter. But lo and behold, they found even more smaller things like the proton and then the neutron within the nucleus of an atom. So the atom had more parts to it. And then, lo and behold, even more things were discovered, such as the proton and the neutron are not even the most fundamental building blocks of matter. They even further break down to quarks, lo and behold, And where do quarks come from? They come from particle physics and an understanding, and a superior understanding of particle physics, which is only possible. Why? Because quantum mechanics is extremely successful, even though bizarre, very bizarre. Quantum mechanics is very successful, and it kept pushing, it kept going, and it unfolded into the entire field of particle physics and the families of particles, including, but hopefully limited to, I don't know, because there's just so many particles, leptons, quarks, and bosons. So basically, now we know. So by the way, thank you so much. Stephen did Stephen did a super chat. Thank you so much, Stephen, my friend. Thank you. So this is what was kind of like going down in the 20th century. Very, very productive century indeed. And it has, of course, oozed into the 21st century, especially with particle physics. We continued to get more and more discoveries in particle physics. And some of the questions in classical physics, where there was this push to have a more broader general theory that can not only explain the classical stuff, but can also explain the quantum stuff, because the classical physicists did not like some of the features of quantum mechanics, like uncertainty principle, the probabilistic nature of quantum mechanics, and so on and so forth. But due to the tremendous experimental success of quantum mechanics, like literally the hydrogen atom is a thing, right? And you can look in it and you can see, oh my gosh, yes, there is the proton, there's the, as you have heavier elements, you even have neutron. Even neutron was discovered later on. And some of the things, this like uncertainty principle, some of the predictions of these things were actually coming true in the lab. Otherwise, quantum mechanics was stomped on enough for it to have died in the 20th century, but instead it flourished and gave us particle physics and the standard model of particle physics, which again includes, of course, the different families of particles, leptons, quarks, and bosons. Leptons would be something like the electron. Quarks are what make up protons and neutrons, and bosons are something like photon, which is the particle nature of light. And I'm just giving you an example out of each of the families. There's more types of particles under each of those families, turns out, as well. Okay, a particle jungle, in other words, is what we get from quantum mechanics and subsequent particle physics, which comes from quantum mechanics. So these are the two sides of physics: general relativity, or just consider it classical physics, which gives us special theory of relativity on this side, and quantum mechanics on the other side. And the two are not seeing eye to eye. So this is what motivated a broader, bigger, more general theory, which can be called sort of the theory of everything, which is what string theory is a candidate for. Now, unfortunately, string theory has its own issues, such as it is not testable. So even though it's been worked on, especially since the 60s, 1960s, and has come a long way, I would say, sure, a long way. I mean, the first sort of little, what do you call, steps into string theory happened as early as 1919 with that Kaluza-Klein stuff that we talked about, where Kaluza and Klein actually proposed one extra spatial dimension on top of general theory of relativity. General theory of relativity already set up the math in a way where you could actually propose extra dimensions if you really wanted to, because remember, general theory of relativity treats time and the three spatial dimensions in sort of an equal-ish footing, in a sort of space-time footing. The dimensions in general theory of relativity are not 3D, they're 4D, because it includes time, and space-time is what's being curved. Space-time, the fabric of space-time is what's being curved with by gravitation. So the way general theory does its math, remember we talked about, it's Riemannian geometry. It's not Euclidean geometry. It's not the planar geometry that we're more familiar with, which is usually 3D or 2D and just involves the spatial dimensions that we all know and love: height, breadth, width, length. Did I say all of them? X, Y, and Z. Length, breadth, and height. Those are what we're more familiar with. And so if you had geometry that kind of just utilizes those three spatial dimensions, then we would be kind of comfortable. But there is geometry that involve more dimensions, extra dimensions, dimensions that we might not be familiar with and might not live in. And Einstein was kind of already doing that with his four space-time type of math for general relativity. And Kaluza and Klein proposed one extra dimension. They were pretty modest with their extra dimension and gave us some stuff back in 1919. And that sort of thing actually made a lot more progress in the form of superstring theory in the 1960s and onwards, okay? There was a time when pretty much it had to take a backseat because everybody's focus was more on quantum mechanics. Okay, and even now, I feel like superstring theory takes a back seat, and quantum mechanics, particle physics, and associated developments actually get more funding. If I'm being honest, but these are the two sides that have been the quarreling two sides of physics, and now we're gonna see what this author, Peter Kohl, has to say about this topic. We're actually towards the very end of this book. It is called Cosmology, a very short introduction by Peter Kohl. And this book is very, very overdue back at the library. So I wanted to kind of finish up whatever his perspective is. Pretty much he's going to be covering exactly what I just said in a summary. I summarized here for you, but we're going to listen to what he has to say from his perspective, because he actually puts some of these ideas and thoughts that we're kind of discussing here into very nice little sentences that are very digestible, very approachable. And it's partly the reason why I've been spending a little bit of time with this book, because of course, cosmology is a little bit of a difficult topic, but if somebody makes it digestible and approachable, then that's always really good. And yesterday we were seeing how he was treating sort of the CMB map and the galaxy map and the distribution of matter in the universe or large scale structure. So we just talked about that yesterday. And this is kind of a continuation of that topic, but more so from a perspective of the theory of everything. Because remember, with the large scale structure, we saw that probably dark matter played a role in forming galaxies. There were certain things that came up during our discussion last night about the large scale structure. And even though it's very insightful, what we also learned is that there are still definitely some pending questions. Okay, so keep in mind that even though we discuss some things and we discuss some things that we understand, there's also things that we don't really know. And I try to let you know and tell you which parts we don't know. So for example, this thing I just mentioned, dark matter, even though we know we need dark matter, we know that dark matter interacts gravitationally, might have had a very important role in large scale structure. Of course, it's present in the halo of our own galaxy and affects things in our own galaxy, such as orbital velocities. These are all facts. These are all sort of what we know, but we don't know the particle nature of dark matter. We don't know exactly what dark matter is made of. We don't have the better insights into what really dark matter is. It's just this matter, extra matter, invisible matter, all words, all synonyms of dark matter that we know interacts gravitationally but does not interact with photons. So we've spent some time talking about dark matter too in the past, but I want you to know that we don't know exactly what it is, and it's a research question. So again, 3 top questions of cosmology are: what is dark energy? We don't fully know, but we do know that the universe is expanding. What is dark matter? We don't fully know what dark matter is, but we do know that it probably played a very important role in large-scale structure, and it does affect directly the velocities of things that are orbiting our galactic center. In other words, making them go too fast instead of slowing down. And 3, actually, just for completion, the number 3 top question of cosmology is actually origin of elements, because believe you me, believe it or not, there are certain elements in the periodic table that we don't fully understand exactly how they're made in stars. But we do know that heavier elements over everything after hydrogen and helium is all made in stars. So hydrogen and helium was given to us as a gift, as a birthday gift from the Big Bang nucleosynthesis, and everything else heavier than hydrogen and helium are made in stars. Okay? All right. So now, with that out of the way, and with that kind of summary for what is going on in physics and in cosmology, let's see what Peter Kohl has to say in his very last chapter of his book on little cosmology, a little book on cosmology. So he should be kind of bringing it all together at the end, right? So that is why I think it's an important chapter to go through. Baji, don't attack her. Baji is fighting with Suji, sorry. So we will bring it all together with this chapter. So hopefully you'll find a lot of value in it, especially if you've missed some of our discussions of string theory and quantum mechanics and general relativity, which we have spent time on in the past. You might want to listen to this with your ears cleared, because this will kind of bring it all together, okay? Thank you. Who is giving me $50? Crazy Sick Wine, how are you? Thank you, Stephen. Thank you. Thank you, Acacio. Everybody feel free. Feel free to do a super chat. Feel free. Did someone call me a man? That's okay. Lethal said you will know when you get out of body experience. No, this is just water. Guys, feel free. Feel free to do super chat. Okay. A theory of everything question mark. Okay, because I wish I could tell you that there is a theory of everything, one and done, but unfortunately, we just have a candidate for the theory of everything. Because if your theory of everything is one that cannot be tested with current technology, it's going to be a candidate. theory of everything, right? So you can still call it a theory of everything, but you just have to either put a question mark at the end of that, or you have to call it a theory of everything candidate. Okay? Your earbuds are making a noise. I think that's a problem with my phone, and I might need to upgrade my phone because it's a secondhand phone with some issues. Okay. The modern era of physics began with two revolutions that took place in the early years of the 20th century. Class, quiz question, what are those two revolutions? Tell me, tell me, tell me. Hi, Austin. How are you doing? What do you think of simulation argument? I don't know. Is that the one where we are thinking about or asking about whether we all live in a simulation or not? The static, I hear it too. Sometimes there is static, guys. I think it's my phone. I think it's my phone. I think I need a phone that does not have this particular defect, but currently this phone does. I'm so very sorry. The static is unbearable, some people are saying. Okay, let's keep going. The modern era of physics began with two revolutions that took place in the early years of the 20th century. One of them involved the introduction of relativity, and it played a major role in the development of cosmology throughout this century, as in last century and really until now. The other major upheaval was the birth of quantum mechanics. By contrast, the implications of quantum physics for cosmology are still far from understood. Okay, so some people like Stephen Hawking actually have used quantum mechanics in a more bigger sense, as in to integrate certain things about black holes, which were traditionally or historically a classical object, if you will. They came from a general relativity or a classical prediction, but he incorporated quantum into black holes, right? So not everybody completely ignores that there is general relativity as well as quantum mechanics, I would say, but to a large extent, the classical physicists don't always consider quantum, and the quantum physicists don't always consider classical. Okay. So, in the world, according to quantum theory, every entity has a dual nature. In classical physics, two distinct concepts were used to describe distinct natural phenomena, waves and particles. Quantum physics tells us that these concepts do not apply separately to the microscopic world. Things that we previously imagined to be particles can sometimes behave like waves. Phenomena that we previously thought of as waves can sometimes behave like particles. Light behaves like a wave. So light actually has both wave and particle duality. By the way, if you, one little trick to remember which one light is going to be more like, if you're considering the very short wavelengths of light, for example, gamma rays, then you have more of a particle nature of light. Gamma rays are almost like particle light, as in photons. Being hit with gamma rays is like being hit with particles. Okay, very short wavelength, very high frequency, almost like a particle, right? And it does have particle nature. If you want to consider light as a wave, then think of it as the bigger wavelengths. If you have longer wavelength light, for example, radio waves, then it is more like a wave and less like a particle, right? So light, for example, has wave and particle duality, but how it shows up or how it manifests in the physical is what I just told you, which is that if you have longer wavelength light, it's going to manifest physically more like a wave. If you have shorter wavelength light, it's going to manifest physically as more like a particle. Okay? So one can produce interference and diffraction effects using prisms and lenses with light. Moreover, Maxwell had shown that light was actually described mathematically by an equation called the wave equation. The wave nature of light is therefore predicted by this theory. So pretty much Maxwell's equations or the E&M, those are all considered classical theories, and it treats light like a wave, okay? On the other hand, Max Planck's work, so Max Planck is a contributor to quantum mechanics. So that work on the radiation emitted by hot bodies had also shown that light could also behave as if it came in discrete packets, which he called quanta. So there we go, light having a wave nature as well as a quantum or particle nature. He hesitated to claim that these quanta could be identified with particles. It was in fact Albert Einstein in the work on the photoelectric effect, for which he won the Nobel Prize, who made the step of saying that light was actually made of particles. So Einstein is therefore called a father of the old quantum mechanics, which deals with sort of this quantum nature of light. So Max Planck may have been the one to have found these discrete packets coming out of the radiation from hot bodies, but it was Einstein that actually gave us the photoelectric effect, and that is what he won his Nobel Prize for. Even though he's more famous for his relativity work, relativity was not really understood very well back then enough for people to have confidence giving him the Nobel Prize for that, okay? So they instead gave it to him for the photoelectric effect. So if you discover something or invent or innovate something extremely out of this world, amazing, and takes a lot of intelligence, maybe also discover some other thing too, and you might just get the Nobel Prize for the lesser discovery, if you will. Not that photoelectric effect is anything small. These particles later became known as photons, but how can something be both a wave and a particle? One has to say that reality cannot be exactly described by either concept, but that it behaves sometimes as if it were a wave and sometimes as if it were a particle. And I was just telling you sort of the manifestation and the trick to understanding when light will be a wave versus when light will be a particle. Longer wavelength light will manifest more like a wave. Shorter wavelength light will manifest more like a particle in your physical experiences, okay? Imagine a medieval monk returning to his monastery after his first trip to Africa. During his travels, he chanced upon a rhinoceros and is faced with the task of describing it to his incredulous brothers. Since none of them has ever seen anything as strange as a rhino in the flesh, he has to proceed by analogy. The rhinoceros, he says, is in some respects like a dragon, and in others like a unicorn. The brothers then have a reasonable picture of what the beast looks like. But neither dragons nor unicorns exist in nature, while the rhinoceros does. That's the duality of a rhinoceros, sort of a unicorn, sort of a dragon. It is the same with our quantum world. Reality is described neither by idealized waves nor by idealized particles. So don't idealize waves or particles. That is not reality, okay? But these concepts can give some impression of certain aspects of the way things really are. The idea that energy came in discrete packets or quanta was also successfully applied to the simplest of all atoms, the hydrogen atom, by Niels Bohr. So again, huge contribution generally in the 20th century to quantum mechanics came in the form of stuff with the hydrogen atom. And that was done by Niels Bohr, really cool guy. And oh, thank you so much. Thank you, Julian. Thank you, Eversor, and thank you, Chickpea. Thank you, everybody, for being here. So the hydrogen atom in the 20th century by Niels Bohr and all of his work in the 20th century led to other aspects of atomic and nuclear physics. The existence of discrete energy levels in atoms and molecules is fundamental to the field of spectroscopy. So this fact about the discrete energy levels within an atom and all of the work that he did to explain the hydrogen atom further really opened up our understanding of, oh my gosh, like this is what goes on in an atom, like all the discrete energy levels and the excitations of electrons and of the ground state. Like if you've ever taken a quantum mechanics class, there's like the ground state, there's the n equals 1, 2, 3, like that, states and whatnot. And those discrete states is what's used in spectroscopy. And remember, where is spectroscopy super duper important? It's very important in astronomy and in cosmology. We depend on spectroscopy. What things spectroscopy or lines in a spectrum, if you will, like people ask, like what line was absorbed when somebody says something like that, what line was absorbed? What they mean is that is how they know what element they're looking at or what element may or may not be present in a star, for example, from spectroscopic lines, because different energies or different discrete energies are absorbed at different by different things and different that's how you can identify the thing which has absorbed or emitted some line on a spectrum. So that is something super important. If you want, we can talk about spectroscopy in more detail, but pretty much spectroscopy itself would not be possible if we didn't have an understanding of quantum mechanics and all these like energy levels that are discrete and within, for example, the atom. So the existence of discrete energy levels in atoms and molecules is fundamental to the field of spectroscopy, which plays a role in fields as diverse as astrophysics and forensic science, and was crucial to Hubble's discovery of the recession of the galaxies. So using spectroscopy, so astronomers have a tough life because their lab is far, far away, right? Like say you're an astronomer and is there a lot of static? Let me put these out. Is it better now? Is it better now? Can you still hear me? Super chat is open for all. Love it. What about now? Julian says yes. Yes, it's better? Okay, give me one moment. Hello, 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 hello. Can you hear me? Welcome, welcome, welcome. Welcome, welcome, welcome. Hello, 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 hello. Can you hear me? Is it any better? Is it happening? Are things happening? Oh, I can hear me from my phone. I think it's sort of working. Eversource says it's okay. Okay. We will keep on keeping on. Sorry about the interruption. You sound like you're in the other room on the phone like that one time. Really? I hear you fine, but you sound like you're in another room. Really? Is it that bad? Oh my gosh. Is it that bad? I hope that the effects of the earbuds, I will just crank up the volume. Yes, please crank up the volume. Is it truly? How is it possible? I don't know what is happening with this phone. I definitely have to get this checked out, but I'm gonna keep going. Hopefully you can hear me. Sorry about the interruptions and the issues. So the idea that energy came in discrete packets or quanta was also successfully
applied to the simplest of all atoms, the hydrogen atom, by Niels Bohr in 1913, and to other aspects of atomic and nuclear physics. The existence of discrete energy levels in atoms and molecules is fundamental to the field of spectroscopy, as we were mentioning. Very, very important in spectroscopy, and it plays a role in fields as diverse as astrophysics and forensics. So all kinds of things utilize spectroscopy. We mentioned it, cosmology, astronomy, all of that. The uncertain universe. The acceptance of the quantized nature of energy and light was only the start of the revolution that founded modern quantum mechanics. So if you think that calling light a particle, even though until that point, by E&M, by Maxwell, light was considered a wave, so we literally got the entire theory of light as a wave from Maxwell and whatnot. And then to call it a particle kind of gives rise to this initial quantum mechanics where light is a particle now. If you thought that that was strange, well, there was much more stranger things to come in the 20th century. Okay, for example, the uncertainty principle, which a lot of even the quantum mechanics contributors didn't even like. So for example, Schrödinger, who is very well known and very well regarded, very well reputed in quantum mechanics as a contributor of quantum mechanics, also actually did not really like that he had contributed to something that ended up having uncertainty and probabilistic nature. So it was not until the 1920s and the work of Schrödinger and Heisenberg that the dual nature of light as both particle and wave was finally elucidated. For a while, the existence of photons had become accepted in the previous years. There had been no way to reconcile this with the well-known wave behavior of light. What emerged in the 1920s was a theory of quantum physics built upon wave mechanics. In Schrödinger's version of systems is described in terms of a wave function, usually called psi, and psi is psi, psi, which evolves according to an equation called the Schrödinger equation. So Schrödinger actually wrote down the wave equation for matter, for a particle. And then someone else, turns out, told us later on, so when he wrote down the wave equation for a particle, he didn't realize that he was going to give us a probabilistic answer for the position as a function of time for a particle, but turns out it was going, he didn't know it, but it was going to be. So anyway, which evolves according to an equation called the Schrödinger equation. The wave function psi depends on both space and time. Schrödinger's equation describes waves that fluctuate in both space and time. So how does the particle behavior come in? The answer is that the quantum wave function does not describe something like an electromagnetic wave, which one thinks of as a physical thing existing at a point in space and fluctuating in time. The quantum wave function describes a probability wave. So this is what I mean. When Schrödinger first wrote down the wave equation for matter, he thought he was writing down the wave equation for matter, and it's sort of like this, like what are they even trying to do in quantum mechanics, right? Like quantum mechanics itself has the clue. Mechanics generally means something as simple as writing down the position of something as a function of time, for example, or even a function of space. You could write down, say, an equation for the moon as a function of time. Now, if you write it down as a classical mechanics equation, in fact, those are written down, right? The equations of motion, the laws of motion, gravitation, etc. Just Newtonian mechanics can give you the function or the equation of the moon's position as a function of time. And what is more, we actually can write that down and get the answer like 1,000 years from now. Like it just works, right? So similar thing in quantum mechanics. Ultimately, they want to write down some equation which gives the position, for example, of a particle as a function of time and also space, turns out. So it's not like they're trying to do something super different or novel. The novelty is that now we're operating at a very small scale. We're operating at the scale of particles or subatomic scales and things that are very tiny, teeny tiny, okay? And the teeny tininess brings into the domain certain extra other things, certain extra features, such as the uncertainty principle turns out, and such as this probabilistic nature, which people were not used to. Because turns out that the Schrodinger wave equation is actually a probabilistic type of a thing. It actually gives you the probability of finding that particle at some point, not the deterministic answer for the position of that particle as a function of time and space. It's the probability of finding that particle, or it's the probability of finding an electron, okay? So in quantum mechanics, we deal in probabilities. We cannot know for sure, like with certainty, we cannot write things down, okay? And so even some of the contributors of quantum mechanics did not pick up on this until later, and it came as a shock even to them. Schrodinger himself was not happy when he found out that the wave equation that he had written down was ultimately a probabilistic object, if you will. So how does the particle behavior come in? The answer is that the quantum wave function does not describe something like an electromagnetic wave, which one thinks of as a physical thing existing at a point in space and fluctuating in time. The quantum wave function describes a probability wave. A probability wave. Quantum theory asserts that the wave function is all one can know about the system. One cannot predict with certainty exactly where the particle will be at a given time, just the probability. Isn't that so interesting though? Isn't that so very, very interesting? It is just the probability. And the shock at that point was that people were not used to that. People were used to getting deterministic answers. If there was an equation written down for something, like the moon, for example, which is a classical object, or say you or me or trees or cats or cars, people expected a deterministic answer. People did not expect, oh, you'll just give me the probability of something happening as an answer. That is not acceptable. People were not very happy about that, okay? The classical physicists. So you can start to see how there was this divide between the classical physicists and the quantum physics, okay, or the quantum physicists. An important aspect of this wave particle duality is the uncertainty principle. This has many repercussions for physics, but the simplest one involves the position of a particle and its speed. Heisenberg's uncertainty principle states that one cannot know the position and speed of a particle independently of one another. Here we go. So not only did people, quantum physicists and classical physicists, have to digest the fact that quantum mechanics was probabilistic, but here was a quantification or a quantization of the uncertainty and the uncertain nature of quantum mechanics in this uncertainty principle formulation or formalization, okay? So there is even a quantification of what this uncertainty is in the form of the uncertainty principle. So this basically says that the better you know the position, the worse you will know the speed of a particle, and vice versa. So if you know the position, you cannot know the speed. Certainly you'll have some limit, some uncertainty limit on the speed. And if you know the speed, you cannot know the position with certainty. You will have some uncertainty on the position. And together, it's postulated in the uncertainty principle. So if you know its speed precisely, then the particle could be located anywhere. This principle is quantitative. I mean, is it really anywhere with equal probability? No. Again, there's a probability associated with finding that particle at a certain position. So it's not like you knew the position was here last you checked and it's going to be somewhere totally different, like on the other side of the universe or anything. Not quite like that. But there's going to be a probability associated with where you expect to find this particle, okay? So this principle is quantitative, does not apply only to position and momentum, but also to energy and time and other pairs of quantities that are known as conjugate variables. There is this concept of conjugate variables in physics. It is a particularly important consequence of the energy-time uncertainty principle that empty space can give birth to short-lived particles that spring in and out of existence on a time scale controlled by the uncertainty principle. So by the by, this whole situation of the uncertainty principle, this whole situation that we talked about, in fact, yesterday we were talking about how nothing can actually have quite a few things in it, especially because of the pair of particles and particle-antiparticle pairs being allowed to kind of go in and out of existence. Actually, nothing can be kind of busy with things happening. We just don't know maybe all the time that that's happening, and until we take sort of a measurement, right? So basically, this situation of the uncertainty principle has a lot of very important consequences. It can actually come to the rescue in some situations where otherwise you would have had a tough time explaining how that can happen, right? So this is the reason why. So if you ever need nothing to have something, then look to the uncertainty principle. This is the reason why particle physicists expect the vacuum to possess energy. So vacuum is technically maybe not always totally nothing. Vacuum could maybe have things going in and out of existence, right? So maybe there is something going on there, full of mystery. In other words, there should be a cosmological constant. So cosmological constant, we talked about it. This is dark energy, and the fact that the universe is expanding calls for something to be doing that. We don't fully understand it. We call it dark energy. Sometimes it's called the cosmological constant. It has a history as an anti-gravity term when Einstein was doing his equations of general relativity. So the name has stuck as the cosmological constant, but more generally, this is dark energy, the topic of dark energy, where we are sort of trying to understand why the universe is expanding. But the uncertainty principle may have something to do with it. We don't fully know about dark energy, what it really is, but that could be something. In other words, there should be a cosmological constant. The only problem is that they don't know how to calculate it. The best guesses available are too large by more than 100 orders of magnitude, but the idea of cosmic uncertainty has scored one notable success. It is thought to be the reason for the existence of small primordial density fluctuations that started off the growth of cosmic structure. Oh wow. So dark energy too has some role probably in large scale structure formation. I actually did not think of that until right now, but it makes sense. That makes sense. So by the way, this book is quite old. So sometimes if it's quoting some sort of number, then please do check the more latest number. We have actually talked about cosmology and some of these numbers from a more modern cosmology book by Scott Doodleson. So it's going to be more accurate from that book. So don't take the numbers here with a grain of salt. Some of the things have actually been updated since the writing of this book. But it's very interesting, the perspective here. A universe running according to Newtonian physics is deterministic, in the sense that if one knew the positions and velocities of all the particles in the system at a given time, then one could predict their behavior at all subsequent times. And this is what I was mentioning with the moon. If you write down the equation for the moon as a function of the position of the moon as a function of time, then that is a pretty deterministic equation. Generally, you can generally you can then predict so this predictive nature of physics, right? I'll write down the equation for something, and that will then predict what's going to happen in the future. This is what people were used to. This is what classical physicists were used to. I'll write down the equation of the position of the moon now, and that same equation can give me, when you plug in for the time later on, it can give me the position of the moon later on, 100 years later. This is what people were used to. This is deterministic. To then go from there to quantum mechanics, where things are probabilistic, was a big jump. A big jump in their, it's an intellectual jump, right? It's this like quantum timeline jumping, basically, of like, we're not used to this, okay? So anyway, the universe running according to Newtonian physics is deterministic in the sense that if one knew the positions and velocities of all the particles in a system at a given time, then one could predict their behavior at all subsequent times. Quantum mechanics changed all that, since one of the essential components of this theory is that the principle that at a fundamental level, the behavior of particles is inherently unpredictable, hence the need to resort to calculations of probability. So how the behaviors happen at those quantum scales is totally different. The interpretation to be put on this probabilistic approach is open to considerable debate. For example, consider a system in which particles travel in a beam towards two closely separated slits. The wave function psi corresponding to this situation displays an interference pattern because the probability wave passes through both slits. So this is a very common little experiment that's done in physics classes, the double slit experiment. If the beam is powerful, it will consist of huge numbers of photons. Statistically, the photons should land on a screen behind the slits according to the probability dictated by the wave function. Since the slits set up an interference pattern, the screen will show a complicated series of bright and faint bands where the waves sometimes add up in phase and sometimes subtract because of being out of phase. This seems reasonable, but suppose we turn the beam down in power. This can be done in such a way that there is only one photon at any time traveling through the slits. So like, what if you tricked this setup and said, we will only allow one photon. One photon. Don't you be leaking anywhere else. The arrival, this can be done in a way such that there is only one photon at any time traveling through the slits. The arrival of each photon can be detected on the screen. By running the experiment for a reasonably long time, one can build up a pattern on the screen. Despite the fact that only one photon at a time is traveling through the apparatus, guess what? Guess how what? The screen still shows the pattern of fringes. So even when you reduce it down to one photon at a time, light still behaves like a wave. How? How? How does it maintain this dual nature of both a particle and wave? How? Who's going to explain it now? Right? It's like if you left this to classical physicists, what are you going to do? What are you going to do? What are you going to do? How are you going to explain this? How are you going to explain the fact that you allowed only one photon through and you still got the wave nature of light as well as the particle nature of light? There was still the dual nature of light being manifested. How? How do you explain that? Who comes to the rescue? Even though it's bizarre, uncertainty principle. So in some sense, each photon must turn into a wave when it leaves the source, travel through both slits, interfering with itself on the way, and then turn back into a photon in order to land in a definite position on the screen. So what is going on? Clearly, each photon lands in a particular place on the screen. At this point, we know its position for sure. What does the wave function for this particle do at this point? According to one interpretation, the so-called Copenhagen interpretation, the wave function collapses so that it is concentrated at a single point. This happens whenever an experiment is performed and a definite result is obtained. But before the outcome is settled, nature itself is indeterminate. The photon really doesn't go through either one of the slits. It's in a mixed state. The act of measurement changes the wave function and therefore changes a reality. This has led many to speculate about the interaction between consciousness and quantum reality. Is it consciousness that causes the wave function to collapse? So, this is where pairs of particle-antiparticle pairs interacting, making a photon, not making a photon, disappearing, this type of thing, this type of shenanigan happens in empty space. It happens. A vacuum is, there's Baji, a vacuum is actually quite busy with things like this. And so now you can imagine that a vacuum can be very interesting indeed. And in fact, vacuum and some sort of negative energy of vacuum is expanding us out in the universe constantly. A vacuum is not so unbusy after all. Just because there's a void doesn't mean that there is nothing going on in that void. There's actually quite a bit going on. And how to explain that is with quantum mechanics. A famous illustration of this conundrum is provided by the paradox of Schrodinger's cat. Oh, I hate this. I don't like when cats are involved in a less than loving way. Imagine there's a cat inside a sealed room containing... I don't like this, whatever. You know what? We'll skip through this. You know about the Schrodinger's cat thing. Only when the room is opened and the state of the cat is measured does it become either alive or the other thing, whatever. An alternative to the Copenhagen interpretation is that nothing physically changes at all when a measurement is performed. What happens is that the observer's state of knowledge changes. This is a real gaslighting of people's... this really makes you question your reality, doesn't it? Quantum mechanics. What happens is that the observer's state of knowledge changes if one asserts that the wave function psi represents what is known by the observer rather than what is true in reality. Then there is no problem in having it change when a particle is known to be in a definite state. This view suggests an interpretation of quantum mechanics in which, at some level, things might be deterministic, but we simply do not know enough to predict. Conundrum. Conundrum. Is she Persian? What do you mean? As in, I guess I know what you mean, but why? Why do you ask? So did some... Are you from Iran? $100 super chat, and I'll get her to wear her pearls next live. I can wear the pearls again, but what's wrong with this? I don't want to wear the same exact earrings every single day, chickpea. I like a little bit of diversity in my earrings. Why are you saying that the pearls are the only ones that I can wear? But also feel free to do a $50 super chat. Can someone do a super chat and I'll answer whether I'm from Iran or not? No one tell him. No one tell him. Don't tell anybody. Am I from Iran? Am I from Iraq? Am I from Afghanistan? How about a super chat? Conundrum. 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 Thank you for liking the live. Yet another view is the many worlds interpretation. So I know that somebody was asking about simulation. I don't know, to be honest. So I think somebody asked me, Common Sense is asking, can you suggest me best book for quantum mechanics, my level? She's from my dreams. Oh, thank you. What's a super chat? A super chat is where you send money on the live. The light is bright with you. Oh, thank you so much. So a super chat is a chat, but it stands out and it gets highlighted. And it's when you donate or send money to support this live and this channel. So somebody asked, about the simulation theory. And my answer is I don't know whether we're living in a simulation or not. I don't think we are. And then, can you suggest me a best book for quantum mechanics? Well, if you want just a popular science book, do you want a popular science book or do you want a textbook? There's an author called Peebles, P-E-E-B-L-E-S, Peebles. And the quantum mechanics book that I studied in undergrad is written by him. Or you could, honestly, you could do Griffith. Griffith's undergrad quantum mechanics. Introduction, I believe it's called Introduction to Quantum Mechanics by David Griffith. G-R-I-F-F-I-T-H. Griffith, just do Griffith then. If you want a textbook on quantum mechanics, then Griffith's. He writes good books. His books are used as textbooks all the time. But in my undergrad, instead of using the Griffith quantum mechanics, we used Peebles. So, why can't we get 30 likes? Okay, thanks. Yes, of course, Griffith. Just do Griffiths. Why not? David Griffith. He writes good books, good textbooks. So another view is the many worlds interpretation. In this, every time an experiment is performed, for example, every time a photon passes through the slit device, the universe, as it were, splits into two. In one universe, the photon goes through the left-hand slit, and in the other, it goes through the right-hand slit. Oh my gosh. If this happens for every photon, one ends up with an enormous number of parallel universes. All possible outcomes of all possible experiments occur in this ensemble. But before I head off into a parallel universe, let me resume the thread of the story. So parallel universes, too, is something that's sometimes suggested or sometimes thought of. It's very sci-fi-y. And again, I don't know really what to think about parallel universes. I don't know if they are a thing or not. Not my sort of forte. Forget what? So I described the standard model of, so this book describes the standard model of fundamental interaction. So we talked about the standard model of particle physics, for example, including, remember, all the particles, the leptons, the quarks, and the bosons, and also the force carriers. So remember that the bosons were the force carriers. And class, what were the fundamental forces of nature? Everybody? So the fundamental forces of nature are, tell me. Eversore. Hi, Free Energy Mobile. How are you doing? Gravitation is one of them. And next. Electromagnetic force is one of them. Strong nuclear force and weak nuclear force. Come on, guys. We've talked about this so many times. So many times. What are the fundamental forces of nature? Gravitation, electromagnetic force, strong nuclear force, and weak nuclear force. Those are the four fundamental forces. The non-gravitational ones are unified at certain extreme energy regimes. Remember this discussion? Gravitation is not unified with those three. And this is the issue. Okay, we will keep going. The three forces it incorporates are all described by quantum theories. The fourth of the fundamental interactions is gravity. So, quantum mechanics does a good job of incorporating electromagnetism, strong nuclear force, and weak nuclear force. Of course, strong and weak nuclear force, these are being discovered well into quantum mechanics and particle physics being a thing. At this point, of course, the standard model is not going is going to do a good job of explaining these things, right? So electromagnetism, those are carried by the force carrier of photons. Photons carry electromagnetism. Electromagnetism, light, remember? Light's particle nature is photons, so photons carry electromagnetism. Strong nuclear force. What? Everybody, listen with your ears cleared. Listen with your ears cleared. Nobody's saying anything correct right now. Listen with your ears cleared. Strong nuclear force is carried by what? Gluons. Weak nuclear force is carried by the W and Z bosons. We've talked about all of this. We've talked about all of this in particle physics class. We've talked about all of this. Everything's made of light. No! Everything is not made of light. No! Okay, so remember class, the non-gravitational forces, electromagnetism, strong nuclear force, and weak nuclear force, these three are unified in particle physics, quantum mechanics. Quantum mechanics has an explanation for this. But what about gravitation? Is there a particle or a particle physics-y or a quantum mechanics explanation of gravitation? No, indeed there is not, and that's an issue. Okay? This is where we fall short in quantum mechanics. So, it is ironic that it is general relativity which really began the modern era of theoretical physics that should provide the stumbling block to further progress toward a unified theory of all the forces of nature. Why? Because general relativity is the theory for gravitation. Gravitation is not explained by particle physics. It's not explained by quantum mechanics. See how that's an issue? Because there's the four fundamental forces of nature. Three of them are unified. Gravitation is not unified with those three. So what's going on there? What's the bigger theory that can hopefully bring it all together? We don't know. We only have a candidate, and it's the time, and it's the that candidate is superstring theory. Tweaking. What's tweaking? What do you mean? In many ways, the force of gravity is extremely weak. It is the weakest one of the four. It is the weakest one of the four. We've talked about how the four fundamental forces are quite different from each other. Gravitation and electromagnetism are felt and known more universally. Like, we're all aware of gravitation. We all feel it. Electromagnetism, I mean, if you get a shock, of course you feel it, right? We feel charge and forces on a charge, etc., etc. Strong nuclear force and weak nuclear force, of course, these are more exotic things that we don't exist in that scale so much. They are sort of things that are happening at much smaller scales, at quantum scale. So they're much more of a quantum contribution to our understanding of this world, if you will. Gravitation is, of course, the general relativity or a classical contribution. It's felt at large scales as well, right? Large scales, hour scales, things like that. But the problem is that gravitation is not explained. Nowhere in quantum mechanics are we getting a particle nature of gravitation, okay? So most material bodies are held together by electrical forces between atoms, which are many orders of magnitude stronger than the gravitational forces between them. But despite its weakness, gravity has a perplexing nature that seems to resist attempts to put it together with quantum theory. So it's true that electromagnetic force is stronger than gravitation, but they're not the same. So remember how gravitation is an always attractive force. always attractive. Two bodies with mass will always be attracted to each other. Electromagnetic force is stronger than the force of gravitation, but it is sometimes attractive and sometimes repulsive. Like charges are repulsive towards each other and opposite charges attract. So gravitation and electromagnetic forces, these are not the same. They're not the same, okay? They're not the same. One is a lot stronger than the other, but first of all, both we're familiar with, and one of them is very universally present, which is gravitation. I mean, electromagnetism is present too, but what kind of, for example, we talked about large scale structure, right? What is sort of really important in cosmology is what's happening in the universe at a large scale. And at that scale, gravitation is a player. It's a very important player. So we would like to understand it better. We really would. And so it's a bummer when it's not explained by quantum mechanics and particle physics, okay? Einstein's general theory of relativity is a classical theory in the sense that Maxwell's equations of electromagnetism are also classical. They involve entities that are smooth rather than discrete and describe behavior that is deterministic rather than probabilistic. So once again, classical will be smooth, quantum will be discrete. Classical will be deterministic, quantum will be probabilistic. Those are the differences. But also, the gaps are there as well. Classical cannot explain certain quantum things, and quantum cannot explain gravitation. That's the issue. So on the other hand, quantum physics describes a fundamental lumpiness. Everything consists of discrete packets or quanta. Likewise, the equations of general relativity allow one to calculate the exact state of the universe at a given time in the future if sufficient information is given at some time in the past. They are therefore deterministic, so deterministic. The quantum world, on the other hand, is subject to the uncertainty embodied in Heisenberg's uncertainty principle. Of course, classical electromagnetic theory is perfectly adequate for many purposes. But the theory does break down in certain situations, such as when radiation fields are very strong. For this reason, physicists sought and eventually found the quantum theory of electromagnetism or quantum electrodynamics. Remember, we talked about QED. It was basically quantifying or unifying electromagnetism with quantum. This theory was also made consistent with the special theory of relativity, but does not include general relativistic effects. While Einstein's equations also seem quite accurate for most purposes, it is similarly natural to attempt the construction of a quantum theory of gravity. Einstein himself always believed that his theory was incomplete in this sense and would eventually need to be replaced by a more complete theory. What do you mean by materialism, really? I actually don't know. What do you mean by that? So, by analogy with the breakdown of classical electromagnetism, one can argue that this should happen when gravitational fields are very strong. So, it's kind of like, does classical theory break down when gravitational fields are very strong, just like the electromagnetic stuff, or on length scales that are extremely short? Attempts to build such a theory have so far been unsuccessful. Now, if you know of any such theory that is successful, then let me know. Although there is nothing resembling a complete picture of what a quantum theory of gravity might involve, there are some interesting speculative ideas. For example, since general relativity is essentially a theory of space-time, space and time themselves must become quantized in quantum gravity theories. This suggests that although space and time appear continuous and smooth to us on minuscule scales of the Planck length, which is around 10 to the minus 33 centimeters, space is much more lumpy and complicated, perhaps consisting of a foam-like topology of bubbles connected by tunnels called wormholes, yay, that are continually forming and closing in the Planck time, which is 10 to the minus 43 seconds. It also seems to make sense to imagine that quantized gravitational waves or gravitons might play the role of the gauge bosons in other fundamental interactions such as the photons do in quantum electrodynamics. As yet, there is no concrete evidence that these ideas are correct. The tiny scales of length and time involved in quantum gravity demonstrate why this quantum gravity is a field for theorists rather than experimentalists. So if you have such tiny scales, that can be kind of difficult to test out. So no device has yet been built capable of forcing particles into a region of order the Planck length or less. The enormous energies required to do this are needed to reveal the quantum nature of gravity. Oops. But that is precisely why so many theoreticians have turned away from particle experiments as such and towards cosmology. The Big Bang must have involved phenomena on the Planck scale, so it may in principle be possible to learn about fundamental physics from cosmology. So it's kind of like we're looking to cosmology because it includes the beginning of the universe where the scales were small. The universe was tiny at one point. It was non-existent at one point, and then the Big Bang happened, and we came to be, as in not we, but the universe started from that point. And there were some very extreme energy scales and time scales or not time scales, length scales at that time. So it's that is almost the better sort of test bed to learn about these things, because now where we are is not a very good length scale or a very good energy scale to understand sort of this theory of everything, if you will. So theory of everything requires very extreme conditions to be tested out, for it to be tested out. And those extreme conditions involve very tiny length scales and very high energies, which, when did that happen? When do we naturally have that happening? In the Big Bang, right? So maybe that is a good point at which those could be studied for, in some way, if we could, study that or probe that, even if it's only theoretical, or if we can get some clue from the cosmic microwave background radiation, which is from, the early universe, not the Big Bang, but it is from when the universe was only 300,000 years old, which is much, much younger than what it is now. So if we can understand anything at all about the Big Bang or soon after, where soon is of course relative, because, hundreds of thousands of years is still, sounds like a long time to us, but it's not a long time with regard to the universe. So this is why people might obsess over the early universe quite a bit in cosmology and look to cosmology to give us some of these answers about the nature of gravitation and this theory of everything candidate that can explain both gravitation as well as quantum mechanics, including, of course, the three non-gravitational forces like quantum electrodynamics, taking into account, of course, electromagnetic force, strong nuclear force, weak nuclear force. We already kind of know, and we actually looked at that it needed supersymmetry somewhere in the picture, but basically the three non-gravitational forces can be unified if you consider very extreme scales of energy and length being very tiny and energy being very high, or very high temperature. So those types of conditions are difficult to reproduce in our current state in the world and in this current universe. But one can imagine that being exactly the similar kind of thing when the universe was getting started in the Big Bang. And so thank you so much for your support. So that is really where it's not just cool to talk about the Big Bang, and it's not just, you know, cool to understand the early universe. It might be the only sort of experimental test bed for us if we can probe it, even if that means that we probe moments after the Big Bang and not quite as far back as the Big Bang. It might just give us the only way to probe such extreme conditions and get these answers out that require those extreme conditions. So we keep mentioning, for example, that superstring theory, we only call it a grand unification theory or a theory of everything candidate because it cannot be tested. It cannot be tested with all its extra dimensions. Some of those extra dimensions are very tiny, so tiny that they cannot be tested, right? This is the issue. We would be, you know, there comes a point where there's enough desperation for a theory of everything where we are willing to accept some crazy theory with a lot of dimensions if it can be tested. But if it cannot be tested, then we're stuck with a candidate versus a real theory. So even that sort of issue, right, the testability of superstring theory, again, might be possible if you can probe back to the Big Bang and moments after the Big Bang, because you might just get the proper conditions for that, okay? Hello, Raphael. Hello, Common Sense. Hello, Eversor. And everybody, thank you so much for being here. Thank you for listening. Thank you for supporting. Raphael Stefanski, I feel like I've seen you before. Are you from Germany or a different country? Welcome, everybody. So, is this undergrad or postgrad level class? I would say it's for anybody, really. It's not, I don't think you need to be in college to understand these topics, because we don't always get into the weeds too much. But some of the concepts are probably more from a postgraduate level. I'm not aware that a lot of these are taught at the undergrad level, unfortunately, because I think that physics gets more fun after the undergrad level. That's why I talk about all of these things, which generally not covered in undergrad. So in that sense, maybe postgrad, but I hope that you don't really need a college degree to follow. So that's really where the motivation is, where cosmology, of course, has taken off as a field in the last 100 years or so, because we have the ability now and we have technology now to experimentally observe much better. We know about lots of galaxies. We know that the universe is expanding. There's always like big open questions, etc., etc. So we have something to study here. But at the same time, remember that a lot of the motivation with the early universe is also because it might give us the only test bed to test out some of these things that we're talking about, such as the theory of everything. Really, can we really do theory of everything without testing it out? Okay, and can we really test it anywhere but other than moments after the Big Bang? So hopefully we get very good at understanding those signatures, those photons, those whatevers from moments after the universe came to be, because therein might lie the answers to these questions that we're asking today, okay? The beginning of time. The presence of a singularity at the very beginning of the universe is very bad news for the Big Bang model. Like the black hole singularity, our two favorite singularities, one is the Big Bang, the other is the black hole. Both are singularities. Both are inconveniences in mathematics, or physics maybe, more than math. Like the black hole singularity, it is a real singularity where the temperature and density become truly infinite. Temperature and density become truly infinite. Singularity. We don't like infinities in physics. So it's a singularity. But at some point you're approaching that infinity, right? So again, it's giving you that extreme stuff, that extreme condition that we may just need to test these things out that we talk about. It's just theory of everything. But at the same time, going to the infinity, once you're at the infinity, once you're at that singularity, you don't feel so good now, do you? Because physically speaking, that is an inconvenience. It is a, oh gosh, my math is breaking down. So in this respect, the Big Bang can be thought of as a kind of a time reverse of the gravitational collapse that forms a black hole. Right? It is pretty much very similar, just opposite way in time. As was the case with the Schwarzschild solution, many physicists thought that the initial cosmological singularity could be a consequence of the special form of the solutions of Einstein's equations used to model the Big Bang. But this is now known to not be the case. Hawking and Penrose the observable universe, it's more the CMB, I would say. Maybe a little farther. Okay. So Hawking and Penrose generalized Penrose's original black hole theorems to show that a singularity invariably exists in the past of an expanding universe in which certain very general conditions apply. From Alpha Centauri, is that what you're saying, Nusrat? Physical theory completely fails us at the instant of the Big Bang where the nasty infinities appear. Nasty infinities, okay? So once again, Hawking and Penrose generalized Penrose's original black hole theorems to show that a singularity invariably exists in the past of an expanding universe in which certain very general conditions apply. And physical theory completely fails us at the instant of the Big Bang. So at the instant of the Big Bang, there is a singularity. And we don't have the means of we don't have the means to really deal with the singularity. We just have to kind of get past it, if you will. Why you pretty and cute? Thank you, Nusrat. So is it possible to avoid this singularity? And if so, how? It is most likely that the initial cosmological singularity might well just be a consequence of extrapolating deductions based on the classical theory of general relativity into a situation where this theory is no longer valid. This is what Einstein says in the paragraph quoted in chapter 3 during the discussion of black holes. What is needed is quantum gravity, but we don't have such a theory. So, again, this whole situation of the quantum, the singularity, right? We depend on, ladies and gents, we depend on general relativity for the classical theory of the beginning of this universe as well as black holes. But maybe that's not such a good idea because these are events or situations or objects or, you know, the Big Bang is more like an event, black hole is more like an object. But these are things where general relativity is kind of breaking down. It can't handle it. A singularity is basically a breakdown of our mathematics or our physical understanding at that point. A black hole, like for example, when we write down the equation for the black hole, we write it down for the Schwarzschild radius for the event horizon. We say that you can go up to the event horizon but no further. If you go inside past the event horizon of a black hole, that there's a singularity there, and we don't know what to do with that. It's actually, it's a flaw. It's a flaw of general relativity. Even though general I don't know what you're saying, Eversor, but yes, please do a super chat. Everybody, thank you so much. Feel free to do a super chat to support the channel and the physics classes. So even though general relativity has had a lot of success, so taking nothing away from general relativity, even if general relativity is, you know, has a couple of issues, doesn't mean that it is still not a great and very successful theory. It has a lot of experimental success as well. Very good at predicting lots of good things, such as, but not limited to, gravitational waves. But a great flaw of general relativity is the singularity at the Big Bang and the singularity in black holes. So it's sort of a limitation of general relativity. So what does that mean? What does that mean? What it means is that we need something better. When something has a limitation, that doesn't mean that all of it is wrong. It just means that it needs a little hand. It needs a little help. So if we had a better, more improved theory for gravitation, something else that can also help out.
So unlock your iPad first.
Oh my God, Siri, shut up. Siri started talking to me. If we had another theory for gravitation, hi Suji Mama, that it could come into play at these difficult and challenging spots in general relativity, such as the Big Bang and such as the black hole, where general relativity gives us a singularity. Okay, so that's sort of the point of it. That's sort of the point of aspiring for another theory, something else, something better, something more general, something more specific. Maybe if there was like a quantum gravity theory or something, anything. Please come and save us from these singularities at the Big Bang and at black holes, okay? Suji Mama is here. So, what is needed is quantum gravity, but we don't have such a theory, and since we don't have it, we don't know whether it would solve the riddle of the universe's apparently pathological birth. So in our math and physics, the universe had a pathological birth. The Big Bang is this pathological birth of our universe. We are good after it, but we're not good at it. Okay? We're good. Come, Shona. We're good at understanding the universe, at least in comparison. We're good. Oh, that's right. You're from Zurich. That's where you're from, Raphael. Raphael is from Switzerland. Welcome, Switzerland. We're okay with and good with explaining and writing down equations for the universe after the Big Bang, but we're not good at the Big Bang. We're not good at the black hole. We're okay up to the event horizon of the black hole. So what that means is that there's a bit of a gap, and we could maybe fill this gap with a better theory, which works well when the gravitational field goes to infinity or is very strong and whatnot, or if the length scale is very tiny, etc., etc. Basically, when conditions are very extreme, we may just want to have a different theory. We just don't have it yet, okay? There are, however, ways of avoiding the initial singularity in classical general relativity without appealing to quantum effects. Firstly, one could try to avoid the singularity by proposing an equation of state for matter in the very early universe that does not obey the conditions laid down by Hawking and Penrose. So, I mean, it's like kind of like when you agree to disagree. The most important of these conditions is a restriction on the behavior of matter at high energies called the strong energy condition. There are various ways in which this condition might indeed be violated. In particular, it is violated during the accelerated expansion predicted in theories of cosmic inflation. Somebody asked about inflation. This might be it. Welcome to Switzerland. Why are you saying boo to Switzerland? Don't do that. Switzerland, feel free and welcome. There are ways in which this condition might indeed be violated. In particular, it is violated during the accelerated expansion predicted in theories of cosmic inflation. Models in which this condition is violated right at the very beginning can have a bounce rather than a singularity. So if you want a bounce instead of a singularity, running the clock back, the universe reaches a minimum size and then expands again. Whether the singularity So it's kind of like not a singularity, but a bounce, like contraction to something minimum, something small, and then expansion if you go to the Big Bang and out. It sounds like a math way of avoiding the singularity, which I guess one could, but at the same time, I think it would be good to understand what happens at those extreme conditions, okay, in general. Whether the singularity is avoidable or not remains an open question. So it's an open question. I don't know. We don't know exactly what happens at the exact moment of the Big Bang. We kind of know after it. Moments after the Big Bang, we're much better at. At the Big Bang, we're not so sure. And the issue of whether we can describe the very earliest phases of the Big Bang before the Planck time will remain open at least until a complete theory of quantum gravity is constructed. So the Planck time is a very tiny time. So until until we're strong at explaining gravity more fully, we might just kind of sort of not know what happened exactly at the Big Bang up until the Planck time, okay? Hi, Michael. The existence of a singularity at the beginning of the universe calls into question the very nature of space and particularly of time at the instant of creation. It would be nice to include at this point a clear definition of what time actually is. You guys ready? Everyone is familiar with what time does and how events tend to be ordered in sequences. We are used to describing events that invariably follow other events in terms of a chain of cause and effect, but we can't get much further than these simple ideas. In the end, the best statement of what is time is that time is whatever it is that is measured by clocks. We talked about the arrow of time and which way is time moving forwards. And remember, we said that there were sort of three ways of thinking about time. There's the cosmological time, and this is the arrow of time in which the universe expands. So if you are measuring time and you're seeing that the universe is still expanding, then you're good. You're going in the right direction. Then there's the thermodynamic way of getting the arrow of time, which is that the second law of thermodynamics says that entropy in the universe always increases. So if you're going forwards in time, or you think you are, and the entropy is still increasing, then you're good. And then there's the psychological meaning of time. According to, by the way, Stephen Hawking, these definitions, we read about this from his book, and he said psychological time is our perception of time, where we kind of remember the past, but we don't remember the future. And hopefully all three are kind of the same, and they are, as far as we think anyways, for us macroscopic beings. And so that is sort of something that we talked about already. I'm going to pause for a bit. So this chapter, this is the very last chapter on this book, which is a little tiny book on cosmology, where I think the author does a really good job of making everything very approachable. So I think we'll finish this up tomorrow. I'll look at your comments and questions in the meantime for the last part of this live. Okay, thank you everybody for being here. So there's just a little bit left. Some more things about time, successes of Einstein's theoretical breakthroughs. He kind of talks about time in the way in which I just summarized it. Big Bang certainly appears to have a preferred direction. The no boundary hypothesis, theories of everything. So We will finish this up tomorrow because it's quite interesting and I want to have full energy when we wrap it up. Thank you so much. Steven, thank you so much for being here. So we will also talk about the anthropic principle. That is also something we had mentioned earlier. So this will be tomorrow. We will wrap this up tomorrow. I'm gonna get my other device opened. So bookmark right here. I'm gonna see, this is the little book that we've been reading. This is called Cosmology, a very short introduction by Peter Kohl. It's very cute. Look at this little tiny book. So we will continue and wrap that up tomorrow. Let me look at your comments and any questions. And chit chat for a bit and then go to bed. And then we will pick it up again tomorrow. Can I ask if you got my email today? I did not, Stephen. I know you said you sent me an email, but indeed I have not gotten it. Raphael, thank you for coming to the live. I think I saw Raphael in one of my daytime kitty cat lives. So thank you so much. It's very good to see you on this live. Hope you enjoyed our physics live. Do you believe in big bounds? I mean, maybe. I think we need to understand gravitation better in terms of quantum mechanics and particle physics, and so I'm open to just kind of studying that and learning more about that. And I'm hoping that those types of things will clarify about the beginning of our universe in terms of whether it was a big bang or a big bounce. There's the kitty cat behind me. You are definitely on kitty cat time. Here's kitty cat behind me. It's got a link to where you can see my finished book, and I plan to start a stream and read my book there too. That's really cool, Stephen. Good luck to you, but I don't think I've seen your book today. I've gotten your emails earlier. How else is she supposed to read the questions? Thank you for stopping by, Raphael. Please like and subscribe. Oh, Raphael said I'm turning 26 years old on September 2. Oh, that's your birthday? September 2nd. A Virgo. Good job, Raphael. Buccaneer Bruce says hi. Just wanted to give you a heads up. Yeah, no, I appreciate it. Stephen. Can you send again? Because I don't think I got it. Ever Eversore, how are you doing? I see some comments. Do a burnout. What? What does that mean? Do a burnout. I'm here before this channel blows up to 50K. Thank you so much, Eversore. Was that Eversore who said that? Thank you, my friend, for your incredible support. Incredible support, you guys. Incredible support. Thank you so much. Muchas gracias. Grazie. Thank you. Please do support. Please do support. We appreciate very, very much. Very, very much. Finish the book. Are you talking to me? We will. Certainly we will. I guess 25 when you asked. Are you Arabic or Latino American? Hi, Nusrat. You're a scientist in astrophysics? Yes. Nausak! My friend, how are you? I'm just saying hi to my friends who joined later. Everybody who joined later on, feel free to rewind. Rewind, like that. Go from here to there. Rewind, go back in time and see the full live. Nausat, how are you doing? Nausat, you're joining from Sri Lanka, right? How are you doing? Michael, are you investigator? Eversore, are you guys fighting? Jeep is jealous because you didn't thank him for his incredible insights. Which ones? He says so many things. Which ones? Nusrat was asking, are you from Mars? Oh, honey. What do you mean? So, by the way, speaking of Mars, and speaking a little bit about astrology, not astronomy, which I know more about, astronomy, not astrology. Mars is the god of war, and it rules the sign of zodiac, or the sign of Aries, the zodiac of Aries. My English is not that good. That's okay. No, of course you can stay. Stay, Nusrat. Stay. So Nusrat, what language do you speak? Maybe I can say something in that language for you. What is your native language, Nusrat? Is it Arabic? Is it Spanish? Is it Persian? Everybody welcome. Marhaba, hello. Hakan says marhaba. Are you Turkish? Marhaba. How are you doing? Russian. Ooh, how to say hello in Russian. Let me Google that. Tamil. Privet? Privet? Is that how you say it? Privet? Is that? I'm from Central Asia. My native language is Uzbek. I love turkey. I don't eat chicken or pork. Uzbek. Uzbek. Okay. Mike D, how are you doing? Are you gonna do a super chat? Privet. Privet. Hello. Das Vidania. Das Vidania. Antalya dan salamlar nasalim niz. Uzbek. Clear Turkish language. Well, hello to Privet to you. Mike D, you did a super chat? Oh, thank you. Chicken is a god. It provides me my daily eggs. Aww. Nausat, thank you for your hearts. Nausat. Aww. Thank you so much for your hearts. And Mike D, thank you. Chicken is a god, provides me with my daily eggs. So Mike D and his eggs have provided us with a super chat. Thank you so much. How very nice of you. Hello Samyang, how are you doing? Michael Green says true. Thank you. Parcel tongue. Are you 17 years old? No. Double that. 17, oh my gosh. I don't eat chicken and you shouldn't either. I also don't eat chicken. I am mostly vegetarian. I eat chickpeas. Chickpeas. 34. Something like 34. Something like that. Sounds more like it. You have a beautiful, intelligent mind. Oh, thank you, Common Sense. A beautiful, intelligent mind. Common Sense. Thank you. I'm 52. Nusrat says, how old are you in Planck time? Good point. How do I meet you one day? We should do a meet and greet. At some point, certainly, I should do a meet and greet here in Boston. Get a picture and an autograph. Aww. Thank you, Mike D. We will do a meet and greet. I'm looking at the comments as much as I can. Who said that? Not Boston. How about California or Reno, Nevada? Okay, we could do it in Las Vegas, or we could do it in the Grand Canyon. We would take a helicopter down to the Grand Canyon, and we could do our meet and greet there. Yes, indeed. California sounds good. California sounds good. Next to those gigantic trees, maybe. What are those trees called again in California that are huge? We could do a meet and greet next to these trees. Or we could do a meet and greet at the bottom of the Grand Canyon, where we would take a little chopper down, and we will open up some champagne at the canyon. We could do that as a meet and greet. Does that help? Redwood trees. Thank you, redwood. California we can do. Okay. California, we're coming. We're coming for the meet and greet in California. I tried to say hi to everybody, but it's not letting me go much farther up. I don't drink, but I can have a shot of Pepsi. Sure, you can do Pepsi. Redwood trees in the petrified forest. Meditation session in California. Yes, exactly. That's a great idea. Meditation session in California. Myrmegonia. What does that mean? There is Baji behind me waking up a little bit. I did not go to Boston College. Edwards Air Force Base. I went to NC State and Ohio State. Okay. Come to San Jose, California, or Sacramento. Okay. I've never been to San Jose, so that sounds pretty good. San Jose, Sacramento. No, I was just reading what Steven said. He wants to go to Edwards. Maybe we can lock eyes. I'm reading everybody's comments. Thoughts on iMessage? iMessage, you mean like, do I use iMessage? I do. My family uses iMessage. Steven Spears, why not Wright Patterson? I used to work at Wright Pat for many years. Goodness. I used to work at Wright Pat. My great uncle was stationed there. Are you Creole? Nusrat is asking all kinds of things. What do you think, Nusrat? In fact, I want to hear more of your guesses tomorrow. You should come to my live again tomorrow, Nusrat, and keep on guessing. The Christianity, the Creole, all of that. You're trying to figure out what I am. You should do more of that tomorrow at my next live. You are handsome. Thank you. Eversource says, I guess. So, anybody else, any other last thoughts, comments? She is Punjabi. I am not Punjabi. Any last things before we say goodnight? Indigenous. Russian, do not understand. Any last thoughts? Good night. Good night, everybody. Like and share with all your neighbors, all your friends, all your family members, all your cousins, all your best friends, least best friends. Children, mother, father, brother, everybody. Please share the live with them. Come with them to the live. And please do like, share, and subscribe. Thank you so very much. Good night. Good night and sleep tight, everybody. Good night and sleep tight until tomorrow. Until tomorrow. Alien abduction thoughts. You are very beautiful. That is power. I guess there is power in beauty. I think there's more power in money, actually. Would you like to do a super chat? Ah. Test pilot. Okay. 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 Let me update the. Thank you for the hearts. Okay. There we go. Esmeralda? I don't know what that is. Who is Esmeralda? I want to change this. Singing. Ah. I do sing sometimes. Deep breaths. Storied life. Thank you, my D. Everyone. There you go. You guys are funny. Somebody said, oh, we talked about that a while ago. We talked about World War II, and we talked about the atomic bomb, which is, I guess, fission. Oh, you're asking about fusion. Well, we constantly talk about that in terms of the stars. Thank you. All right, everybody. Thank you so much. Nusrat, we will continue tomorrow. Everybody, let's continue tomorrow. We will be back here on the live stream tomorrow to finish up the book and the cosmology story that we're currently talking about. And hope to see you, everybody, there tomorrow. Hope to see everyone tomorrow. Please do come to our live stream tomorrow night. We will finish up this cosmology discussion and we will look at your comments and thoughts and things like that. And we might even have time for a little bit of particle physics and such, okay? So once again, thank you so much for your support and thank you for being here and see you tomorrow. Mwah. Good night. Sleep tight, okay? Bye-bye. Bye-bye. See you tomorrow. Bye.